Welcome back. I consider the following diagram to be the most essential in all of mathematics because it's three different takes on a difficult concept. No one perspective is enough to capture what everyone's trying to talk about. This is the notion of equality, putting things into categories, and functions. All right, behind me is what I call the equality resonance circle. What it is it's three different takes on the same difficult concept. So no one take is enough to explain it. And in fact, the whole point of this resonance is that you often are given only one version of the story, and you succeed if you're able to move around to one of the other configurations. So let's take a look at what this means. Let's start with the concept of an equivalence relation. I'll remind you what that means. What we're trying to do is say, what does it mean for two things to be equal? We could, for example, think of a photograph. If we take a photograph and save the file, we have some choices to make. Perhaps we save it as a JPEG, or a PNG, or a BMP, or a GIF, or many other formats. There are certainly many technical differences between these formats. The changes in how fast we can read the files as well as the size of the files are some of the things you might be able to measure as different. But if we put them on the screen, the point of these compression systems is that they should be visually more or less the same, with maybe small artifacts that we're willing to forgive. So the concept here is that when we would say that these two formats are equivalent, we're saying that the quality of the image is the same. They are not the same files, so there is a notion in which they're different. The fundamental concept of an equivalence is that we can use the data interchangeably. What do I mean by that? In symbols, I would write something like this. This rule is sometimes known as the Leibniz law or the indiscernibility of identicals. Let's take a minute to expand on what this means. Whenever I write the symbols A is equivalent to A prime, and then I run through all properties P, it's clear that I must mean in some context. There is no list of all the properties in the universe. Instead, our universe has to be shrunk to things we care about. For example, let's imagine that A and A prime are two files that save the same picture. For example, we took a photograph with a digital camera and we offered to save it in two different formats, PNG and JPEG, just for the illustration. The idea here is that all the visualizations of this should be the same. I can't really tell. Once I open the file, they're interchangeable to me. If the context I care about is that the images look the same, then JPEG and PNG are completely interchangeable. The differences in quality of image are very minor to most human eyes. That's partly by the design of both formats. However, if I change the context and start to ask questions about the engineering, I might find several differences. For example, maybe JPEG is a smaller file, or maybe PNG is faster to load. There can also be situations of licensing. One format might require me to use private software and the other one might be open source. So therefore, we can start to imagine that data often have many different fine details that can make them different. But we don't necessarily need to care at every moment about all those details. By discussing an equivalence, we're saying that for the details we care about, we can use them interchangeably. Now, when we do this, a few consequences happen immediately. For example, we can always say that A is interchangeable with itself. That is what we call reflexive. A is equivalent to A. Furthermore, it's a symmetric relationship. If I can use A instead of A prime, then I can use A prime instead of A. This is what's known as the symmetric law. We can swap it by a symmetry, and we don't see a change in the effect. The final rule is known as the transitive law. Here what it means is that if A is equivalent to A prime, and A prime is equivalent to A double prime, then A is equivalent to A double prime. If I can use A prime instead of A, and I can use A double prime instead of A prime, then I can use A double prime instead of A. For most applications, these three rules are enough to guarantee that we'll be able to check all the properties that we care about. After all, in order to notice a difference, we would have to pick up somewhere that something changed. If, for example, we saw that sometimes A wasn't used the same way, we wouldn't call it a property about A. And if we saw that there was an asymmetry, we wouldn't call that equivalent either. So it's a consequence that whenever every property is used interchangeably, then these three properties are used interchangeably. Somewhat surprisingly, in most logics, the kinds of things we do to create properties is a complex mixture of smaller properties like ands, ors, nots, and implication. And if those are the only ingredients we're using to create new properties, then it suffices to just check these three properties because they will mix together to prove all other properties are preserved as well. So for the purposes of mathematics, we declare that something is an equivalence whenever these three rules are satisfied. My own preference is to learn the first rule of the Leibniz law as the reason we would want equivalence, and then discover as a consequence that these three rules are enough to test it. Once we have this, we enter into this equality resonance by passing to a new structure. This is the structure we talked about when we partitioned. So what I have here is the symbolic way of describing the words that we had in our previous description. Part 1 says that every element in our partition is some subset of our A. Remember, 2 to the A is our power set, the set of all possible subsets. Part 2 says that if we took all the parts together and overlapped them, we would end up covering all of A. So every point is represented in some classification. Part 3 says that we're not overlapping any particular parts. If P and Q are two different parts, so they're not equal, then they will intersect with nothing in common. So they just perfectly cover the space. That was the description of what we called a partition. There's a nice mathematical abbreviation of those properties. It's called a disjoint union. And we had a whole video on this construct because it's one of the important type formers in early set theory. Here I'm using the notation with a square union sign. What it says is that every element of A exists in exactly one of these P's. There can be no overlaps and no points missing. When a disjoint union is equal to a set A, we call that a partition of the set. What connects equivalence relations to partitions is that every equivalence relation guarantees the existence of a particular partition. The relationship that connects these two is that from every equivalence relation, we always guarantee the existence of some partition. We don't know which yet. The parts of this partition are what we call equivalence classes. They are all the values in A that are equal to our value little a. We can tick off the properties of a partition by looking at these three conditions of an equivalence relation. For example, from the beginning, we see that everything lies in A, so 1 is satisfied right away. In order to get 2, we need to have every point in A have some equivalence class that contains it. Well, since A is equivalent to itself, this equivalence class always contains the representative little a. Not surprising, perhaps, but important to verify. We now have 1 and 2. The last rule is that we shouldn't have any overlaps. That is, if we have two equivalence classes which are different, they shouldn't have any values in common. So if we have the equivalence class for A and the equivalence class for A double prime, and those intersect non-trivially, we need to have them be equal. Remember, intersecting non-trivially means that there's a common point. Let's call that common point A prime. Since A prime is in both of these, then A is equivalent to A prime. But A double prime is also equivalent to A prime, and it doesn't matter which side we put the equality on, because of the symmetric law. But now that means that we've set up our transitive law as well. We have A equivalent to A prime and A prime equivalent to A double prime. Therefore, A is equivalent to A double prime. Well, since A and A prime are equivalent, that means their equivalence classes are identical. We now see that the third condition is also satisfied. So we now see if we have an equivalence relation, we get a partition. But often in real life, we have to work in different ways. Often an equivalence relation is something we think about conceptually, such as, are there supervised and unsupervised users? But to actually locate them, it might be easier to go off and run a machine learning algorithm to create a partition, a classifier. Once we run this algorithm, it gives us a partition, but not with an associated equivalence relation that we can reason about. But this is where we get into our resonance. What we do is we observe that all partitions, whether from equivalence relations or somewhere else, end up combining to create new functions. In this case, the function is simply to output the unique part of the partition that contains our element. Since every element is in some part of the partition and no partitions carry the same elements, that is unique. This makes a function from our set A into the partition. In fact, it's a surjective function because everything in P is a subset of A, so it'll be hit by something. In fact, this injects a brand new idea. What if we just look at arbitrary functions on A? If I take an arbitrary function from A to B, then I claim we can produce an equivalence relation. The way we create the equivalence relation is simply to identify that the outputs are the same. Given a function f from A to B, we create the equivalence called mod f, where we say A is equivalent to A prime if f of A equals f of A prime. That's a test in B. This is an enormously powerful tool because functions can represent arbitrary programs. So if we're successful in creating an equivalence relation, then we'll also be successful in creating a new data type, the partition, and we could return it to a new surjective function, and the whole process would start all over. This idea is one of the main ways that we create equivalence classes, through little programs that send our data to something else, a classifier function. Now, as we said before, we can't stick around to check every property doesn't change under our equivalence, but it's enough to check that these three properties are there in order to get the same conclusion. For example, why is A equivalent to A? Well, because f of A is equal to f of A. And if A is equivalent to A prime, then f of A equals f of A prime. Equality is an equivalence relation, so that's symmetric. We swap it in B, and then we rewrite the story as A prime is equivalent to A. Likewise with transitivity. In all matters of equivalence, our main goal is to take the equality we're targeting and shift it to a place that already has an equality. We can just borrow the properties from there. Functions let us do that. If B already has a nice equivalence we're willing to borrow, we can lift it and apply that equivalence on A. Now, in order to see the elegance of this, let's erase some of the details. So let's put it together. At the top, we have the constant of equivalence relations. These are relationships on a set A which compare two values and decide whether we're going to call them the same. Let's suppose that we've been given an equivalence at the start. For example, we could say two users are considered the same for advertisers if they're both unsupervised, but they wouldn't be the same as an unsupervised user. Once we've settled on that equality, we're able to look at our users and partition them into equivalence classes. We gather together the ones that have the same qualities, the same equality. Sometimes we'll start with an equivalence relation where we already understand the concepts of what we want to say is equal. Other times we stumble upon a partition instead. For example, a machine learning algorithm might simply classify points in the dataset together if they're statistically similar. Whether I've created parts in a partition by some alternative method or through an equivalence relation, I now have the opportunity to create a function from A to B. Not just any function, a function into P. That function into P simply sends A to the corresponding part that it lives in. Since every data point is in exactly one partition part, this will be a unique function. That function will furthermore be surjective. But if we had any function, we could always create the fiber equivalence. Do the two data points end up at the same place once I apply f? That turns out to be an equivalence relation. If we've gone full circle, we're back at an equivalence relation. This type of reasoning is known as a resonance, because once we apply the technique to get inside the circle, if we continue to apply the technique, we'll end up at the same place. We just go in loops. What this says in spirit is that while we might change the actual representation of our data, all three methods are studying the very same concept. And the value is that we might think about it in different ways. For example, we might want to talk about equivalences because we want to treat our users the same based on whether they're equal to each other as a profile. But we may need something like a machine learning algorithm to produce a partition that honors that equivalence relation. Finally, to actually activate that in our usage, we'll want a function that singles out how to pick those equivalent choices. Without this resonance, we wouldn't have the flexibility to do all three. I consider this resonance to be the heart of most of the challenges in mathematics. It's because it's three different takes on a concept. It means that the concept itself is somewhat difficult to understand. Otherwise, we wouldn't keep reinventing different ways to see the same question. By having created three looks at the same data, we're giving ourselves more power in reasoning about it. It's too much to suggest that you get a tattoo of this resonance, but it would be great if you memorized it. Until next time. That's how you take care of your chalkboard.